Let us talk about calculus. I guess you all are familiar with the equation of a line. We all have studied it in our school days, right? We write it something like y equals x, where if we have this line, then at every point on the line, the value of y depends on the value of x. For example, if x equals 2, then y equals 2, right? This relationship shows how y changes as x changes. But this kind of relationship is easy to visualize because it's a straight line, constant and predictable. Now, imagine you're a curious thinker in the 1600s, when the world was just beginning to explore the motion of planets, the falling of objects, and how things move and change over time. Straight lines didn't cut it anymore. Things in nature didn't always behave predictably, or move in straight lines. Think of a ball rolling down a hill, or water flowing into a basin. How do we even begin to describe such motion mathematically? Let's go back to the straight line for a moment. A straight line has a very special property. It has a constant slope. The slope tells us how steep the line is. That is how much y changes when x changes. For y equals x, the slope is 1, meaning for every 1 step forward in x, y goes up by 1, right? Now consider another line, y equals 2 times x. The slope of this line is 2, meaning that for every 1 step forward in x, y now goes up by 2. In other words, this line is much steeper than the first one. Therefore, slope is like a measure of the line's steepness. It tells us how fast y is changing compared to x. Now, imagine a situation where the slope is 0. For instance, if you have a line like y equals 3, a horizontal line, then we know that the slope of this line is 0, because y doesn't change at all, no matter how much x changes. On the other hand, if the slope is a very large number, the line is super steep, almost vertical. I think you understood my point. But then, someone like Galileo might come along and say, what about something like y equals x squared? That's not a straight line. It's a curve. For example, we all know that distance equals speed into time. Now assume you are running at a constant speed, say 2 meters per second. So d will now be equal to 2t, where d is the distance and t is the time, right? Now if I draw this graph where I put time on x-axis and distance on y-axis, then we get this straight line, and the slope of this line will be the same as your constant speed of 2. But now, assume you start running in a race, and instead of maintaining a constant speed, you begin slowly and then gradually speed up. At first, you might cover only 1 meter in the first second, which is equal to this point, then 3 meters in the second, and perhaps 6 meters in the third second. The distance you cover is no longer proportional to time, and the graph of distance versus time will no longer be a straight line. It will be a curve. In this case, your speed, or the slope of the graph, or the steepness of the curve, keeps changing. At the start, your speed or the slope is small because you're running slowly. As you speed up, the slope becomes steeper, showing that the distance you cover in each second is increasing. Therefore, at any given moment, the slope of the curve represents your speed at that exact point in time. Back in the 1600s, this was a huge problem. The slope wasn't constant anymore. People could draw the curve, but they had no idea how to calculate the slope at any specific point on it. And then came geniuses like Isaac Newton and Gottfried Wilhelm Leibniz in the late 1600s. Both of them, working separately, came up with a groundbreaking idea. Instead of thinking about the whole curve at once, they zoomed in really close, so close that the curve looked almost like a straight line. This is how the concept of the derivative was born. We all know that if we have 2 points like this on a straight line, then its slope is given as y,